So in this section, we're going to look at area in between curves, and we're talking about two separate functions now, f and g. And as long as f is greater than g over some closed interval, then the area between the curves is the integral from a to b of f minus g. And the thing you're going to like about this quite a bit is that there is some work that you're going to have to do algebraically, but a lot of this you can punch into your calculator and get an answer. You can also do it the long way, which is great. I recommend that as well. So we're looking at these two functions right here, secant squared x and sine x. And when we're looking at these guys, I'm just going to label this right guy over here. This is y equals, this is f2. And, whoops, not f2, but f2 of x. f2 of x, and he is sine x. Okay, so what we're going to do is we're just going to look at these two guys and find the area in between the curves. So pi over 4 is actually about halfway in between. It's roughly, let's get a black ink here. It's roughly right here. So, you know, when I draw this vertical line up, then the question that I'm really asking is, you know, what is the area between these two curves right in here? Okay. And the cool thing about integrals is it lets us do that really without a lot of a problem. We just need to know which function's on the top. In this case, it's the secant squared. So what do? We integrate from 0 to pi over 4. And we're going to integrate secant squared x minus sine x dx. And this is really integrates pretty easily anyway. Secant squared just becomes tan x. Negative sine x becomes plus cosine x. And we're going to integrate it from 0 to pi over 4. It's a really disgusting pi. Let me make him. Okay. And that's really all there is to it. You can also punch this into your calculator. You're going to get some sort of decimal. When you work it out longhand, you're going to do stop minus start. And when you do stop minus start, you're going to get the tangent of pi over 4 plus the cosine of pi over 4 minus the tangent at 0 plus the cosine of 0. Okay? So the tangent of pi over 4 is 1. The cosine of pi over 4 is the square root of 2 over 2. Minus, and then the tangent at 0 is 0. And the cosine at 0 is 1. So what you're going to end up with here is square root of 2 over 2. And if you do it on your calculator, you know, and you're checking your answer somewhere, probably the answer is going to be square root of 2 over 2. But if it isn't, if you punch it into your calculator, you should get 7.7071. So that's it. That's all there is on these kinds of things. And some of them can be quite complex, but for the most part, you're just looking at the area above, the curve above, minus the curve below. And so keep it simple, figure out which is which, and set your integral up accordingly. Alright, on this question then we're going to find the area of the region enclosed by the two functions. And a little bit different than from the previous problem is we aren't told an interval to integrate from. So we know that when we integrate, we want to go from start to stop, and then we want to do the upper function, not f of g, but f of x minus g of x. So we want to go top minus bottom. And in this particular function, the top stays on the top and the bottom stays on the bottom. But we need to discover the points where these guys intersect. Because where those two guys intersect is going to be my A and my B. And so to do the legwork on this first, what we're going to have to do is just take 2 minus x squared. That's one of my functions, and in fact it's in blue. And the other function is negative x, and it's in red. and I'm just going to set them equal to each other and solve this question. Once this question is solved, I'll have my two values of x. So on this, I'm just going to go ahead and move over the x squared and the 2. So I'm going to have 0 equals x squared minus x plus 2. And I can factor this guy to x minus 2 and x plus 1. Now, if you're working this on your calculator, you can also find a point of intersection by just plugging these numbers into your calculator. And if you can, if you look on there, you can see that, where we would possibly have those points of intersection. So, but it looks like it's going to be when x is equal to 2 and negative 1. Okay, those are going to be our points of intersection, and so now we're just going to integrate, and we're going to integrate from negative 1 to 2, and we're going to integrate the upper function, which is going to be 2 minus x squared, minus the lower function, which is negative x. And always, 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 always put parentheses in there so that everything is sorted out correctly and organized appropriately. And then when you do this, you can either use your calculator, do it by hand. Both ways are good. You should be able to do both ways by now. But you're looking at an integral from negative 1 to 2 of 2 minus x squared. Well, that's bad. 2 minus x squared plus x dx. So if you're going by hand, 2x minus x cubed over 3 plus x squared over 2. And you're going to integrate from negative 1 to 2, from start minus stop. If you just punch this into your calculator, or you integrate it by hand, either way, where you should end up is 9.5 units squared for the total area under that curve. On this problem, we have 2 cosine x and x squared minus 1. And again, what you want to do is you want to use your calculator if you can. And on the top, we got the cosine x, and on the bottom is the x squared. So we're just going to look at the integral of the top minus the bottom. So 2 cosine x minus x squared minus 1 dx. The only thing is where to integrate from. So what I would do is just on your calculator, use your calculator and find these points of intersection. They're going to be the same on both. One will be positive, one negative. And when you do that, you're going to find that this is the point, 1.2654. And this would be the negative version of that, negative 1.2654. So we're going to just integrate from those two values. And then punch this in your calculator. Again, it's easy to do. It doesn't take a lot of time, and it'll get you a good answer. And your answer should be about 4.9949, depending on where you round. And this is the area under the curve in units squared. And again, that area is this whole space right in here. Now we're going to look at finding the area of a region that's in the first quadrant, bounded by the x-axis on the bottom, and on the top by the square root of 2, and then, or the square root of x, and then also bounded by x minus 2. So what we're going to do is put a line right here for my bottom boundary, and we're going to try and find the area of this region right in here. Okay. Well, you'll notice that my region changes from equations that are on top. And so on the first part of my graph, I'm looking at just the square root of x. And so from 0 to 2, I'm looking at the integral of the square root of x. And how did I get 2? Well, I looked at the place where my linear part of my graph showed up, which is the x minus 2 part. So when x minus 2 is equal to 0, That's when x is equal to 2. So that's this guy right here. The second integral that I'm going to look at then, and I'm going to add it to that, is going to go from 2 to 4. And it's going to be the top minus the bottom. So again, we're going to have the square root of x now, because he's on the top, minus x minus 2.
No, he's not. He's not doing that. He's left.
So I find this other point over here by setting the two equations equal to each other, the square root of x and x minus 2. And when I do that, I'm going to square both sides. And don't forget, when you square a binomial, you get a trinomial. So I have x equals x squared minus 4x plus 4, which is going to be 0 equals x squared minus 5x plus 4. And so x squared, this guy factors then. This guy factors to x minus 4, x minus 1. And the only point of intersection that we're going to see is at 4 because of where we're located on the x-axis. Keep in mind this square root graph curves around the bottom down here. And so if we were to continue that graph, that's where this 1 comes from. But for our purposes, the 1 is not going to be included, just the 4. So that's the setup on the second problem. And then you can either integrate by hand, or use your calculator. Either way, using the calculator now is going to be a little bit easier, a little less time consuming. And when you punch all of this in, you're going to end up with 3.3 units squared. And if you do it by hand, you're going to have 10/3 units squared of shaded region inside those curves. Sometimes you can integrate with y, and it's a lot easier to do. So if we took that same exact problem that we just got done solving, and we looked at the same exact area, which is going to be above the x-axis in this first quadrant, and is represented in here, then if we want to integrate with respect to y, then what happens is, the big change is, we look at change going this way, and this change becomes dy. Okay, so all we need to do then is just make all our equations say x equals, and once those equations say x equals, then this becomes not a problem. So where I've got y equals the square root of x, this becomes y squared equals x. Where I have y equals x minus 2, this becomes y plus 2 equals x. And so now what I can do is integrate with top minus bottom. In other words, now instead of top minus bottom, I'm going to do right minus left. So we would integrate, and we would follow our same rules of integration, except now they're going to be along the y-axis, so we'll call them C and D. So we would be right here, and this would be C, this would be D, and we're going to go with the right minus the left, dy. And so when I integrate now, I'm going to go from 0 to 2, but I'm going to go with y plus 2 minus y squared. You can punch this into your calculator also, or as you can see right here, it's not a very difficult integration problem. You're going to end up with y squared over 2 plus 2y minus y cubed over 3, and we're going to integrate from 0 to 2. Either way, you should get 10/3 here, or if you punch this into your calculator, 3.3 repeating. And it's just another way that you can integrate. It's not hard, and sometimes it can actually be quite a bit easier. Alright, so here's a region for us. Y equals x cubed and x equals y squared minus 2. I've gone ahead and graphed this, and I related it all back to y equals so we can put it on the calculator. And on this guy right here, when you solve him out for y, you're going to add 2 to both sides, and then take the square root. So that's going to get you the plus and minus the square root of 2 part. The question is whether we should work this out with relation to y or work this out with relation to x. And if we did it with relation to x, there's a couple places we may have to change things around a little bit and look at some different points. And so we would have to look at 2 separate integrals. If you relate all this, and the 2 separate integrals would occur right here on this line right here. So I would look at one integral on this side, and then I would look at an integral on this side. And so that's going to be 2 different sets with 4 different numbers. However, if we twist this and relate it back to, let me just undo some of this here. If we twist this back to y, and we can make these say y equals, then I'm going from this point right here to this point right here, and it's just one integral instead of a pair. And again, I can subtract from left to right because the red one is always to the right of the others. And so I'm going to do that, and I'm going to take my top equation here and cube both sides. So y to the 1/3 power is equal to x. I've already got my other x equation right here. Okay, and I'm just going to integrate, and I've shown us our points of interest, so I'm going to integrate on the y values from -1 to 1.79. And it's going to look like this. Integrate from -1.79, -1 to 1.79. And I'm going to do the right side minus the left side. So that's going to be the integral of y to the 1/3 minus y squared minus 2. And you can punch this into your calculator, and it's, again, you could do either way. It's easiest maybe to punch it into your calculator. It's not a problem. And then when you get done, you're going to be somewhere around or close to, depending on how many decimal places you carry through, 4.215 units squared of area between the graphs right here. So this is kind of what you're looking at, and this is an example of when it's actually going to be easier to integrate with respect to y than with respect to x.